screen. Dr. Omar, let me introduce you first. Of course, it is my pleasure to introduce Dr. Omar Elbagalati. He is with us today, and he will talk about a very interesting topic. Omar has long expertise in pavement management systems and the application of pavement management. Dr. Omar graduated with a BSc from Mansoura University, as well as his Master of Science was from Mansoura University as well. Then he joined ASU for several weeks for training, and then he moved to Louisiana State University, where he got his PhD with Dr. Mustafa Saifi, and his PhD was about pavement management system. I believe it was about the rolling wheel deflectometer. Omar, correct me if
Yes,
I'm
that's correct. That's correct.
Yeah. And then after graduation, he worked for several entities. I guess you joined. Was it Austin DOT first, and then Dynatest?
No, it
What?
was, so Dynatest was my first job, then ARA, then city of Fort Worth, Texas, and now with Michelin.
Okay. So our presentation today, it will be about a very interesting topic, as I told you. And Omar, you can start, and please give us like a brief about yourself first, and then you can start your presentation, and the floor is yours.
Yeah. So first of all, as Dr. Sharif said, like I'm a son of Mansoura University. I'm very proud and honored to be a graduate from Mansoura University. And Dr. Sharif and Dr. Ala, they actually my professors. They are my teachers, and I have to say that I have learned a lot. And my life in US during my PhD was way easier than other students coming from other countries, just because of the rich background that I learned during my bachelor and my master while being in Mansoura University. And I have always to mention that. Right now, I'm Director of Market Insights and Research for Michelin. Michelin, if you are familiar with, it's the tire company, and they have like a data science arm when it comes to mobility and artificial intelligence. And I'm their Director of Market Insights and Research, which makes me a little bit close to what is going on in the mobility and data industry. What are the new devices? What are the new techniques? What are the new challenges in the market, and how we are tackling these? So today I gathered something for you. I called it Advanced Techniques for Subsurface Pavement Investigation. So it will be like a mix of what I got through experience during my PhD, during my work in the government, in consulting business, and what I'm doing right now. When we talk about advanced or new techniques, so it will not be all like 2024 new, but I would say you will see some advanced techniques that are not like very common. Some of them are maybe are common here in US like for the last 10 or 15 years, but mostly you will see something new today. So let's go ahead and get started. The presentation topic is basically advanced technique for subsurface pavement investigation. And what we will go through today, I will first go through, okay, what is the difference between surface and subsurface? What we exactly mean by subsurface, and I will go through a little bit of an overview and why do we need to do subsurface pavement investigations. Then I will go through like three techniques that I call them as examples of advanced techniques. So we'll talk about smart geogrids, we'll talk about ground penetrating radars, and smart geotagging or smart tagging. So I guarantee you, like smart geogrids and smart tagging, you will see something new that I'm 100% sure you didn't even see, because they are even still in the production and testing phase here in US. They are not yet commercialized. GPR is a little bit older than them, maybe have been around for 20 years, but still considered new. So first of all, what exactly do we mean by surface versus subsurface, or what is subsurface? So if you look at the pavement, you can look at the pavement from two different points of view. You can assume that you take a cross section in the pavement, like the image we have on the left hand side, when you can see the thicknesses of the layer. You can see the pavement structural composition, the crushed stone, the base layer, the sub-base layer, the subgrade. You can see like pipes and utilities and so on. So this is what we call by subsurface, like what is happening underneath my asphalt or concrete layer, what is happening underneath my surface layer. And then you have on the right hand side, basically, if you are looking from a bird eye view, you are looking from the top, and all you can see is your pavement surface. So what we will focus on today is the one on the left. How can I investigate the subsurface condition of my pavement? So let's dive deeper a little bit and see some examples of what I can get from the surface pavement surveys and what I can get from the subsurface pavement surveys. So from the subsurface, like what is classified as subsurface survey? If you are interested in knowing your sublayer thickness, that's a subsurface pavement survey. Or maybe it's a sublayer stiffness or subgrade capacity, for example, like your CPR. Or maybe you are looking for moisture, like you trying to determine the moisture content of some of your layers, or even you are looking for some escaped moisture from like maybe a pipe leak. Voids, utilities, where are my electricity cables, where are my water and wastewater pipes, and so on. So all of this is classified under the subsurface pavement survey, and this is what we will focus on in this lecture. On the right-hand side, this is where we have our surface. So what do I get from the surface survey? From the surface survey, you get to all the other good stuff that most of you should be already very familiar with. Okay, what is PCI, the distresses, like cracks and deformations and potholes. Or maybe you are trying to determine the friction, surface texture, and of course, roughness, well, the International Roughness Index. You are trying to calculate IRI. What we will go through today will be more focused on what we have on the left-hand side, the subsurface pavement surveys. So if we want to even classify subsurface pavement surveys deeper, I would say some of them are non-destructive and some are destructive. And we today also will more focus on the non-destructive side. So what is destructive versus non-destructive? Basically, from what the name implies, if it is destructive, it means that you are causing damage to your pavement section while doing the test. While if it is non-destructive, you are not causing any damage, basically. So the test itself is not harmful to the pavement. Some examples of these are like the nuclear gauge that is used to determine the soil density or the sublayer density. GPR, which we will go and talk about it in details in this lecture. Falling weight deflectometers are also non-destructive testing that are used to determine the asphalt and the sublayers moduli, if you will. On the other hand side, you have the destructive testing, and as I mentioned, these are the testings that you do, and they are causing damage to your pavement, like taking a core out from the pavement, or doing DCP testing to get like your base layers and sub layers, the CBR, or maybe you open a trench in the pavement and you do your investigations from there. So what we will focus today is subsurface, and not just subsurface, we will actually focus on non-destructive subsurface surveys. So why I do subsurface survey? So I explained this twice. We need subsurface survey twice, one from like the academic perspective or the scientific perspective, and the other one is like from a logistic perspective. So from academic perspective, let's look at it one by one. So one piece of information that you may get from doing a subsurface survey is your layer stiffness. So you get the stiffness basically, which is the strength of your layers and sublayers. You can do this either non-destructively by using the FWD or the falling weight deflectometer, or even destructively by doing the DCP or the CPR testing. So why will I need something like this? If you want to do an overlay design, you need to know first what is the strength of your sublayers. If you are calculating a structural number, which actually you will need it if you are doing an overlay design and you are using 1993 actual design method. If you are doing what we call PCR, ECR analysis on airports, which used to called ACN, PCN, you may be more familiar with the term ACN, PCN, but recently the FAA has changed that system to call it ACR, PCR. And if you are trying to determine the remaining surface life of your pavement, to do all of that, you will need to know the E-moduli of your layers and sub-layers of the pavement. Okay, so something else that you will need to be, that you might be interested in is the layer thickness. Why would I be interested in the layer thickness? First, all of the above. If you are doing overlay design, structure number, ACR, PCR, remaining surface life, you need to know your layer thicknesses. Maybe you are doing quantity calculation for bidding. For example, you are hiring a contractor to come and completely reconstruct the road. So if they are reconstructing the street or they are reconstructing the highways, you will be removing the materials and you will pay them based on the quantity of the materials that they are removing. So if I can know in advance what are my layer thicknesses and calculate my quantities, I can plan better and allocate budget better, knowing how much I'm estimating to be paying this contractor. Or maybe you are doing some roadway widening. So imagine you have a 2-lane highway with a shoulder, and then you decided that you need one extra lane. So in this case, you need to know what are my layer thickness, especially on the shoulder side, so that when I build the new lane, do I need to remove the shoulder completely and pave a new lane, or maybe the shoulder thickness are almost the same as the lane thickness, and I don't need to remove the shoulder. I just pave more on the same thickness. So if you are widening your road, you better know what you already have. Some other investigations that you can do is basically voids and moisture. So you will need to know about where are the voids inside your pavement, where are the moisture. If you are doing some sort of forensic analysis, you are trying to get a root cause analysis or rehabilitation recommendation, meaning you have a pavement or a segment of pavement and it keeps cracking or it keeps failing, and you want to determine what exactly is the cause. So when you do a rehabilitation and you recommend how it is repaired, it is once and for all. So in this case, okay, I need to know, is it just the load is higher than the pavement capacity and I just need like to add an overlay, or maybe there is a pipe down there and it is leaking and this is causing voids and moisture, and no matter how many overlays or how many inches of overlays I will add to the pavement, it will keep failing. So this is what we call root cause analysis. I want to dive deeper in the pavement and know exactly why it is failing. So when I determine a rehabilitation recommendation, it is like the right treatment and it will last. Then we have utility allocation. What by utility here we mean water pipes, wastewater pipes, yeah, cables for electricity, cables for the internet, like the fibers and so on. Why do I need to do this? Let's imagine you are doing any construction activity in your street and you need to plan and coordinate. So for example, if you know that you are going to reconstruct a street and then you figure out that there is a water pipe and this water pipe is in bad condition and the water department at some point they will need to go and replace it. So you better coordinate with the water department from the beginning. Say, hey, water department, in 2025, we are planning to reconstruct this street. Would you team up with me and we add one more line item in our contract for a water contractor to change or replace this water pipe? So we only pave the road once and we allocate funding better. Or maybe the water pipe is in good shape, but it's shallow enough that while you are doing your FDR full depth reclamation, for example, or you are milling, you may hit this water pipe, or you may hit this fiber optics line for the internet, or this electricity cable, or telephone cable, or and so on. So in this case, you give heads up to construction crew, you give heads up to maybe the city or the public work department to know that there will be some power outage, or you coordinate better how to avoid that, or use an alternative line for this region until you are done with the construction and so on. And also for cost estimation, if you hire the contractor to remove the pavement or reconstruct the pavement, and they didn't account for that there will be a pipe that they may need to replace, or they may need to avoid, or something like that, you will not have accurate estimation for the cost, because contractors will not do anything for free. They need to know what exactly they are signing for. Then we have stresses and strains, and we will dive deeper into this when it comes to the smart geogrid example. So basically, it allows you for structural monitoring. It allows you to be proactive. If you know what's happening in your pavement stress and strain wise, you can figure out when it will fail before it basically fails. And then we have, even if we went to concrete and bridges, you can allocate where are you rebar, and are they rusted? Do they need maintenance? And based on this, you can do both, like root cause analysis, and also you determine the right rehabilitation recommendation for this piece of pavement, or this segment of pavement, or a bridge. So this is the why we do subsurface surveys in terms of scientific side. But also there is a logistical side. Okay, why do I even need to calculate thickness? Isn't the thickness something there in the design? Like, why I don't just open an as-built drawing, or I open the design documents and I figure out what is the thickness of my pavement? So there are, like, I would say, three main reasons for this. So number one, I call it different entities. So within the same exact piece of pavement, or within the same exact pavement segment, you will find out there are so many players who have the authority to work on your pavement. So maybe you had the road, and it is already designed, and it's already constructed, and the department that constructed this road is the roadway. I would just give it a name, like the roadway department. And then you have another department inside the city, or inside the county, or المحافظة, for example, and they have an in-house group. By in-house here, I mean they have the authority to go fix the road without contracting out someone. They already have the equipment and materials, and they go and do it. Usually, these two entities, even in US, they don't communicate to each other. So they may go and add 1 inch or 2 inches of overlay, but they don't communicate. So now you have the as-built drawing, and you assume that this is the final, and I only have maybe 6 inches of asphalt, while in reality you have 8. But you don't know that because these two departments never talk to each other. Maybe you have a water pipe that got broken, and the water department went and cut the road and fixed the pipe and put a completely different pavement section with different materials, with different thicknesses, and you never know about it. So the papers are saying something, and what's in reality is something completely different. So because so many different entities are working on the same pavement segment, and usually they are not communicating with each other, you cannot just rely on what you have on paper. Also, sometimes the data is very outdated. So these as-built drawing are like so old, or they are non-user friendly. So they are in the archive department somewhere. They have never been digitalized, so there is no easy access for them. They are hard to read. The ink has already weared and teared, and you cannot read through it. Or sometimes we even rely on employees and because of employees rotation. So you always trusted someone who knows the information, and this someone retired, and they didn't handle the data accurately to whoever employees came after, and so on. And then you start lose this information generation after the other. Also, you may have some new circumstances happening to Europe. Maybe you are now seeing heavier traffic, which means you have more damage. You have been through some climatic crisis like flooding or freeze, or maybe there have been any subsurface damage that you are not aware of. So this is why you need to do your FWDs and determine your like CPR and so on. So let's go and talk about our first example here for something advanced when it comes to surveying your pavement subsurface or getting information about pavement subsurface. So I trust most of you have experience or at least have heard of the term geotextile or geogrid. So what is geogrids? Geogrids are basically this mesh that usually it is, I believe it's a poly material. You can imagine it as steel reinforcement for your soil and granular layers. It is not, of course, steel, but it is doing the same function that steel reinforcement is doing in concrete, in soil, and in base layer. So if we look at the section on the left bottom hand side of the screen, you can see on the very left, this is your pavement section, for example, if you are not using any geotextile. And on the right hand side, if you use the geotextile or use the geogrids, because you are adding this extra enforcement, you can actually end up with less thick pavement section. It has so many benefits. Basically, it's reducing the construction cost, reducing the construction time, even the environmental footprint, because if you are reducing the quantities, it means less water required, less fuel, less electricity, and everything, so less CO2 emissions and so on. But we are not here to talk about geogrids in their main function, which is making the road more stable or making the road more strong. We are talking here about leveraging these geogrids by installing some strain sensors and temperature sensors in top of the geogrid itself. So if you may have heard of a company called Tensar, which basically in US, they are the biggest producer for geogrids. So they came out with this idea, which is not commercialized yet. If I will be, so these geogrids, imagine them, they are coming in rolls, and you are spreading these rolls over your subgrade layer or between the base and the asphalt, as the asphalt layer while construction. So if I can have some sort of sensors in top of the geogrid and inside these rolls, when I stretch them over my pavement, I don't actually need any extra effort to add the sensors. They are already on the geogrid itself. So you are leveraging the time that you are already installing the geogrid in the pavement by adding these sensors in the factory from the beginning on the geogrid. So the system that they have produced is basically simple. You have the strain sensor on the geogrid. It's on the pavement. Everything is wireless, and it is being powered by I would say by the motion or the vibration coming from the vehicles moving above it. So a vehicle is passing by, it producing enough vibration to power up these sensors. So the battery will never, so there is basically no battery. The battery will never die. It can last for maybe 20 years. And then you have an edge device on the side of the road that is capturing the data wirelessly coming from these sensors, and then it sends it to the cloud. So that means you have real-time stress and strain data being uploaded to the cloud every time a vehicle passes over this piece of pavement. And what we can use this for is what we will look at here. So you can see on the top right corner of the screen, this is how the strain sensor look like on top of the geogrid. And as I said, you are here utilizing the geogrid as a base for these strain gauges. It will be under the pavement, either between the subgrade and base layer or between the base layer and the asphalt layer. It is completely wireless, so there is no wires between the sensors and the edge device. Everything here is wireless. And the edge device itself, as you can see in on the image on the bottom right corner, it is even powered by solar energy. So everything here is like you don't need any extra source of electricity. The edge device is powered by solar system. The device itself, the strains ourselves, strain gauges, they are powered by the vibration coming from the vehicle. I'm not an electrician, but I will try to do my best to explain how exactly are these powered by vibration. So when a mechanical load pass over the sensor, it makes this like piezoelectric transducer to move, and when it moves and vibrates, it creates a current, and this current push the electrons to basically power your string gauge, which will be enough power to transmit the data to the edge device. And if there are no vehicles passing by, you are not getting any power and you are not charging your system, but you also don't need to, because you don't need to send any data. So how does these strain gauges work? And I know this might be complicated a little bit even for myself. So basically, inside every one of these sensors, there are 7 gates. Every gate is calculating the amount of time a strain is passing as a specific threshold. So maybe if you have very low strain, only gate number 1 will work. If you have a little bit higher strain, then gate number 1 will work and gate number 2 will work. If you have very, very high strain, then all the gates from number 1 to number 7 will work. But number 1 will have the highest amount of time and number 7 will have the least amount of time. So what do we get from here? If you put your geogrid and you have the sensor on top of it, and you can see that always only from gates 1 to 3 are capturing data, and gates 4 to 7 never capture any data. That tells you that this road will never fail. Basically, you have very low strains. You don't have any big trucks, or this is like very rare to have like big trucks on this road. If you see that gates number 6 and 7 are always being activated and you're collecting data, that means you have like very high strains. This may be coming from the material getting weak, or because you have like higher loads. But this is not what's important. What's important is what you see on the very right hand side, these slopes. Once you start seeing the slope, which is basically what you are looking here, this is the accumulative strain with time. So this will always go up. However, if it is going up with the same slope or a decreasing slope, it means that your material is not getting weaker. However, when you look at here, like in gate number 7, I don't know if you can see my mouse. If you see the last slope on gate number 7 and you see the slope is starting to increase upward, that gives you an indication that your material at this exact point, your material started to be damaged. So the pavement surface will still look very good. If you did a PCI survey, it will still be 100, but you know that things started to be bad down there from the tensile strain perspective. So this is another way of looking at it. Like imagine a car just passing by. You are measuring your response over time. If you have like when the loop passes, because it's at its highest, all the gates will be activated. Gate number 7 will measure the least amount of time, and gate number 1 will be the highest, and so on. And once you see this D6 and D7, once this number start being like so high, it means that your pavement started to get weaker. So this system was actually tested in France. So they have this testing facility out there, which is I found to be fascinating. If you give it a look, they have this wheels are rotating over the pavement. It was not built just for this type of like if you have a sensor. Basically, let's say you came out with a new mix design or a new pavement material, and we want to figure out if it will last or it will have a good performance or not. You go to their facility and you pave a section and they keep loading it. This is what we call ALF, like accelerating loading facility. Basically, you are simulating maybe 20 years of traffic on a piece of pavement, but you can do this simulation maybe in 3 or 6 months. There are so many different, I would believe, shapes of this accelerated testing facility. Like this, in France, they are using this rotating one. Some others, you can imagine like a big truss with a wheel going like back and forth and back and forth, which they call it HVS, Heavy Vehicle Simulator. But they have used this in France for the smart geogrids, and they started to test the damage, and they start to do some FWD testing in I would say with the same time that they are capturing the data from the sensors. So the FWD testing, what we do something called the back calculation. So basically, you know the deflection, you know the pavement thickness because it's controlled environment. You can back calculate your layer stiffness, and you can determine exactly when will your layer stiffness go lower, which means you started to have some damage in the subsurface layer. And you have this strain data coming from the strain sensors. You can then correlate. This is how we figure out, okay, at this slope of gate number 7, we can imagine that damage has a start because we had some FWD testing happen, and we did some back calculation, and we started to do this correlation between stress and strains coming from the sensor, strains coming from the sensor, and the FWD back calculation. So the system has been tested in real roads, has been tested in controlled environment in both airports and in I would say like in highway systems, and it was also tested in the lab. So basically, these are usually the steps that you go through when you have a new product. So you came with an idea, you prove the concept, and then you start testing it in the lab, and then in controlled environment, and then at completely outside, like on real life road, basically. So why we are actually doing that? Like, what is the benefit of calculating the strain and figuring out what is happening before anything happen? Like, if my road is in good condition and I can see it from the surface, why I even care about monitoring it that early? I would assume, let's say you started to feel some pain, and you are getting older, and you are just waiting, doing nothing. You don't do your checkups, you are not going to your doctors, and so on. After a little while, you will start getting really sick. Maybe you will have like a chronic headache, or you have something, and then you will end up basically maybe with a very expensive treatment or going through a surgery. This is like style of life. There are some people, they decide that this is my style of life. I will not go to the doctor until I am really in pain, regardless of the what will happen based on that. And some others, they are different. They every 6 months or every 1 year, they go to the doctor, they check their blood cholesterol, they check their weight, and they do the checkups. And based on that, the doctor will start fine-tuning them. Hey, I see your blood sugar has started to increase. You need to change your diet. I see your cholesterol is going up. You may need to do more workouts, and so on. And these people will usually live longer and healthier. It is the exact same thing with pavement. And even now, you don't even need to go and check up, or even wait 6 months or 1 year between the checkups, because now you have these watches. So with the watch, it is monitoring your heart rate, monitoring your sleep quality, monitoring your oxygen level, how many steps do you walk, and so on. So imagine that these smart geogrid sensors are exactly similar to having the watch. It is always telling you what is your condition, what is happening down there. So you can imagine a piece of pavement which looked very good from the outside, similar to someone who feels okay, but if they went to the doctor and they run the numbers, they will found that they have some health issues. So imagine your road telling you, I will get sick soon, before they really get sick. So instead of going to the surgeon or going through the very expensive kind of treatment, you can actually figure it out with a little bit of medicine or pills, and you fix things way early before they need more money to fix. So as I mentioned, when you have something like that, when you have a new product, you need to actually test it in the field. So while I was working with City of Fort Worth, we did this pilot project with Tensar. We had a concrete pavement project where we were replacing some slabs, and they came with the geogrids, and we started installing them with a sensor. If you look at the image number 2 and 3, when this is in full product, when this product is finite, it will not look like that. So they give us some pieces of the geogrid with the sensors on top of them. However, when this is in full production, if this was not a pilot project, you will see the whole mesh has this geogrid all over, and there will be like hundreds of these sensors. But because this is a pilot project, they give us like small pieces of geogrid with one sensor on each, and we were like trying to see what will the data look like. If you look at the left-hand side image, you can see this pole here with the solar energy. This is the edge device. This is the device that's harvesting the data coming from the sensors. In addition, we also installed some cameras that has the ability to identify traffic and classifying them and see, okay, this is like an 18-wheeler truck, this is like a school bus, and this is just a regular passenger car, so that we can correlate and look at data coming from the sensor and what type of vehicle was passing by. You don't really need to do this if that was like a real life project, but because that was a research, we trusted that this will give us more and more information about the behavior of these sensors. I forgot to mention to you that these sensors are actually also measuring temperature. So if we look back, you will see some of them are gray and some are red. So the gray ones, they were measuring temperature, and the red ones, they are the one measuring the strains. So while you are in construction, for example, because you can imagine now you have your sensors, some of them are open to the air, some are covered by the concrete layer, some are covered by the subgrade layer, sorry, the base layer. So they will be during construction, they will be at different temperatures. That's why you can see here it is like fluctuating. Once you are done with the construction and everything is under the pavement completely, you should see like these temperatures all coming together and be very close to each other. And why measuring temperature is important. Again, like if you recall in the very beginning, we said some extreme weather condition can cause some damage to your pavement. So you can figure out if it is freezing outside, it doesn't mandate that it is actually freezing inside the pavement. So you can know actually, is the subgrade being frozen or not? Or maybe you are in summer and temperature is very high, and then you figure out that one of the sensor is reporting low temperature than usual than the other sensors. That can be a good indication that there is a water leak happening, and due to the water leak, temperature are reducing, and you can go and investigate further and figure out what is going on before it becomes like an extreme damage. So if we look at the strain sensors during the testing, and remember, this is cumulative strain, which means it will never go down. It will only just go up. So in the beginning, you put your strain sensors, nothing is above it yet. You are almost at zero. Then you put your base layer, it will jump up because now you have a constant weight on top of the strain sensors, but then you are waiting until you add your concrete and you compact it, so it increases again, and then until you open it to traffic, it should keep being horizontal like this. So we installed the sensor in a street over there in Fort Worth called FA Boulevard. These were like different locations of sensors we installed over there, and we started capturing data. You can see here the data was making sense. We installed it in around March, April, so temperature was down. Then during summer, temperatures was going up until August, September, and then in October started to going down again, which makes that tells you that the sensors are making sense. Like nothing weird. The temperature in August, for example, is not lower than the temperature in October, and so on. And these are the strain sensors. Sensor number 62, for example, here you can see, as we mentioned, it will always keep going up, and it is going up with a reduced slope, not with an increased slope. And if you looked at gates number 7, 8, and so we used like 9 gates, not just 7, you will see we are only picking data on G1, G2, and G3 and 4, and then everything else is almost zero. That tells you you have very low strain, your pavement is in very good condition, and nothing to worry about so far. And this is normal because this is basically a new pavement. It has been there for less than a year so far. And another temperature sensor, again, everything looked normal. And here, the same thing. Strain are going up. It's a little bit, the slopes started to increase, but you have your G7 and 8 and 9. They are not really increasing yet, so you are in safe. And then we found this very interesting one. If you look at this one, you will see you have activated more. So this is our first time to see G4 picking, and you can see the slope here between August 27 to September 10 has increased a lot. So this tells you something wrong is going on. This is a new pavement. It's still under warranty. It shouldn't see anything yet, any cracks. What is happening? What's going on? So that was fortunate and unfortunate in the same time for us in the city. Okay, am I getting damaged that early of life of my pavement? What's going on here? So we went to the field and we started to see these hair cracks. And this is the beauty of that is imagine when you build this road, the contractor will give you 2 years of warranty. If you have this hairline crack, you will never notice it. No one of the citizen will ever complain about it because it is so small. So it will only start getting bigger after the street is out of warranty and the city will need to pay from the taxpayer money to fix it. However, if you have a sensor like this and you see this signal and you go out and you see the hair crack starting to initiate, you can go to your contractor and say, hey, Mr. Contractor, we have been only 6 months or 1 year in the pavement life, and we started seeing the cracks. The pavement is still in warranty. Please go ahead and replace this slab for me on your own cost. So this is a typical real life example from the field on what the usefulness of these sensors down there. So Tensar, they have also some future plans for these sensors. They are planning to install them between the slabs and the base layers on these types of mesh that you are looking at, not on top of a geogrid. And these sensors are a little bit different. They are not strain sensors. Think of them as sensors when like a pressure cell. So when they are squeezed, they have like some sort of a hover sign signal coming by. So if you look at the number 1, 2, and 3 here, imagine you have these 3 sensors. If the slab is in 100% contact with the base layer, every time a vehicle is passing by, it squeezes the sensor between the concrete layer and the base layer, and it will produce this black hover sign here that you see. Okay, so it means we are in good contact. What is happening to the slab over time? It has what we call like curling and warping. So the slab starts to have this like some sort of V shape or U shape. What will happen when you have this U shape or V shape? Of course, you have to know that this image is exaggerating. It will not look like it will not be that easy or obvious to see it with your bare eyes in the field. But this what will be happening. It is a little bit V-shaped or U-shaped, and now these sensors, these black sensors, when a vehicle is passing by, are not squeezed enough as before between the concrete layer and the base layer. So what will happen to this black signals that we were receiving at a high amplitude? The amplitude will be lower as these like red examples, which will tell you there are some voids between the concrete layer and the base layer. This void, maybe it's like a real void, or because of this like warping and curling stress, so behavior. So you are again getting an early sign that damage is about to happen before it even happens. Some future plans are also to use it in like in railway and also to add some moisture sensitivity on top of them. I would like before we jump in, because I believe there's a lot of information to digest Dr. Sharif, do we want to stop for 5 minutes and take some questions?
How far are we to the end of the presentation, Omar?
We are almost 50% now.
50%. Okay,
Are we
so
planning only 1 hour or 2 hours? I don't know.
1 hour and a half would be fine, and then we will leave like maybe like 10 minutes for questions. But if
Okay.
you're okay, we can allow a couple of questions right now, and
Okay.
then we can move forward. Any
Okay.
questions so far? Any questions? Rahmat.
Hello, Dr. Omar.
Hello.
Please, what is the required distance between sensors?
Again, so this is still in not commercialized yet. So, and again, also there is, I will not even imagine there will be a required distance. It's basically based on how frequent you wanted your data. Is for you maybe 50 feet is enough. Someone will say 100 feet is enough. So there will be, I don't think there will be a requirement.
Okay.
Also, you may imagine, okay, I can do it every 100 feet, but what if one sensor fails? So you will reduce it based on how much failure is happening to these sensors. You cannot imagine that. Yes, the battery will last for 20 years, but will the sensor itself really last for 20 years before it goes out of service or being damaged or anything?
My experience with the string gauges, because we've used them before, but that was like a lab type. And usually when it happened several times when we were installing them, we were measuring the tensile strain at the geogrid like base configuration. In the lab, we built like a large prototype of a pavement section, and we were applying some loads using like the plate loading test. And during the installation, some of the strain gauges, we usually had them failed just after putting, the
Yep.
layers of the materials above them. So I guess this is still questionable if you want to go ahead, and the long term, I'm sure that they are being used in like field sections, for example, in INCAT and other facilities. But the long term, like maybe 10, 20 years in the future, I'm not sure about that yet. Maybe you can add about this a little bit, Omar.
So if I 100% agree with you, Dr. Sharif. If we go back to, I actually took out some slides, not just for the sake of the presentation. If you look at here, I believe we had 15 sensors installed in this piece of pavement. I believe 2 of them are already failed by now, and the project was done in, I believe, in 2022. So yes, they are still very prone to failure even right after the construction. But if you have 15 and you are still having 13 out of them running, it's good. But yes, they are very easy to broke, not to break.
Yeah, but the idea is actually very nice, as you integrate a lot of work that have been done about like energy harvesting from pavement, in addition to like installing some sensors, integrating all these systems together, collect the data wirelessly, use the energy generated from the movement of the vehicles to collect the data. I guess all this is really very nice, and the future applications are tremendous.
Yep. Thank you, doctor. So the other one is a little bit less sophisticated, I would say, and it will go way faster than the smart geogrid. It's called smart tagging, and it's by a startup company called Infratico in Michigan. And basically, what they are doing here is they created some devices. I would say it's like a little bit bigger than a coin size that can basically store some data on top of them, and you can read this data back using RFID, as we can see as we will see in next slides. What is unique about these small devices, they are very strong that they can handle the heat of the asphalt mix, and they can handle the weight of the construction equipment. So what is that exactly? So if you're looking at the left hand, you can see these two devices. One of them like is a sort of a coin, and the other one is in a sort of like a strip. So these devices are strong enough to handle the heat from the mix and to handle the weight of the equipment. What does that mean? Imagine now I can add some data on this coin and say, okay, I'm paving a road. It's in Mansoura City, Galaa Street, and today is October 26, and the temperature is this and that. The pavement design section is this and that. My mix design for the pavement. This is the type of bitumen that I'm using. Any data. What is the name of the contractor? The name of the engineer? Whatever. And you literally through this coin inside you're mixing the asphalt mixer. So when you pave the road, you can go back 20 years after and you read this data back. So you are using your road, your pavement itself as your database. So instead of the data being saved in the cloud or in papers or in hard drives, you are using your pavement as your hard drive. You are saving the pavement data on the pavement itself. So there are two ways to read this data back. If you recall, like when you go to the supermarket and you are scanning like these devices that scan the barcode, you can have like a similar device and you walk with it and you harvest the data. Of course, you will need to be maybe 6 to 7 feet close to where the device location is. Some more advanced options that come with it, like I will create an accessory. You will have like a bigger device that if you just put it inside a vehicle and you drive the vehicle over the road, it will start harvesting back the data from all the devices that are installed out there. So this is an example from data sheet that comes from the manufacturer with what information you want to put there, like project name, date of placement, and you don't have to every time through the coin inside the asphalt mix. You can actually add it on top of the base layer before you pave the asphalt layer or pour the concrete, for example. So you can know even where is the exact location of it. Is it like at the lane number 1, lane number 2, at the shoulder, and so on. So you add, if it's a concrete pavement, what is the pavement, what is the design, cement content, what is the type of aggregate, how much water is in there, if you have run like a slump test, what was the concrete temperature. And this is 100% customizable. You may be interested in any other sort of data. You can customize your form and put whatever data you want on it and then save it to the sensor. So as I mentioned, you don't need really to throw it inside the mix. You can, as on the left hand side, you can see the image. You can put the sensors on the granular layer. You can actually what this second image is showing. You can move with the compactor on top of the sensor, and it will not break. And crazy enough, this sensor is $1, so it is really cheap one. I don't know how they could come with. Well, I think this is why it is very innovative. You have something that's strong and that cheap, basically. So you pave your road. You can even do some marks to remember where are your sensors that you have installed in the past. And you can even, let's say you have some changes. Maybe you add 1 inch of overlay 1 year later. You can come back and get the device close enough to the sensors and you override the old information that were there. So it is not just once and for all. No, you add the data during construction, and then after construction, if something changed, you can go with the same device that you read. You can even write and overwrite on these sensors. So again, when I was in Fort Worth, we did like an actual project when we were paving, and we used these sensors and we saved the data on them, and you can see here the technician is basically inputting the data, like the pavement temperature and so on the sensor before construction starts. So this will get us, okay, why we are doing this? First of all, as I said, because different entities are working on the road and so on. This is stories that I told in the beginning. Then it is hard to track some critical information and to trace the material properties and so on. Also for construction quality. So you assume something on the design, and then when you start construction, you may not get the actual product, maybe not getting the actual mix, or it is not paved at the actual temperature or compaction and so on. So you have the ability to write what really happened on these sensors instead of what was supposed to be happening. Now also you should have heard about like cloud cost and data storage cost and so on. So in this case, you don't even have to have your data on the cloud and pay cost to save them, or even be prone to hacking. So basically, no one can hack these devices because they are not accessible through the internet or anything. You have to have the RF device. This is the only way that you can mess up with the data. And you can now match what the material properties that you want it to be there versus what is actually down there. So they are low cost. As I said, it's like $1 per device. Maybe for your first project, you will pay a little bit for the IRF reader, especially the one on the car, and maybe the license for the software. But then every time else you want to use these sensors, you are just paying for the cost of the sensor itself, which is basically very cheap. The reader is fully integrated with the tags. We call it like smart tags, and they can read and write on top of them. Software is 100% customizable. You can add whatever types of data that you are interested in. There are no batteries. Again, it is actually powered by the device. So if there is no IRF device next to it trying to read or write on it, they are never used. So the battery will last forever. If you are reading from it, the device while reading or writing on it is charging it. So it will basically last forever. Oh, this is what the manufacturer is claiming actually. Then we will come to ground penetrating radar, which I would say it's an advanced technique, but it is not a new technique. It has been out there maybe for the last 15 to 20 years actively. However, I would say it has been, I would say, in the last maybe 5 years, getting more trendy, which means if in US you have like 50 DOTs and 5 of them were doing regular GPR surveys, and maybe other 5 or 10 were doing it only in like few projects, and the others are not using it at all. Today, I would say, no, this utilization rate has increased a lot, and everyone in US now using GPR surveys, and the market is actually booming for GPR. So what is GPR, or what's ground penetrating radar? And that gets me back again to Dr. Sharif. The first time I heard about this device was when I was in last year as a student, undergrad student in Mansour University, and Dr. Sharif actually he is the one told us that there is a device called GPR. So when I came to US, I had this interest to know more about it. So again, I have to say thank you to Dr. Sharif, especially I have worked with GPR a lot. Like a big portion of my consulting resume is based on the projects I have done with GPR. So GPR, you think of it as it's a device, and it is producing sonar waves, basically. And it has a transmitter which produces the sonar waves, and it has a receiver that reads it. So if you look at the transmitter here, the antenna of the transmitter, it is pushing these waves to the pavement and also to the air. So there is time. So waves moves everywhere, right? So there is time between the wave leaving the transmitter and going to the receiver, and the other time between the wave hitting the pavement surface and going back to the receiver. So by calculating this two difference in time, you can know basically how fast is your waves transferring through the pavement section. So every time this wave is going into two different densities. So from air to basically your asphalt layer, there are two different densities. So there will be a difference in the velocity. And then when it moves in the asphalt, it will have a different density than moving in the base layer. And when it's moving in the base layer, it will have a different speed or velocity than if it is moving in the subgrade layer, and so on from the subgrade to from the sub-base layer to the subgrade layer. If you take a cross section and you look on the other side, you will see like these peaks in amplitude at the interface between every layer and the other, between the air and the top layer, between the top layer and the subsoil, and so on. So by tracking these waves, you can figure out the depth of the layer. Am I right? No. So what you are looking at on the right-hand side here is not the depth of the layer yet, because if you look at the z-axis, you will see it says time. So what you are actually measuring right now is time. You know how much time did the wave spend through the asphalt layer. You know how much time did the wave spend through the base layer. How much time did the wave take to pass through the subgrade layer. But you didn't get the depth yet. So the raw data coming from GPR, this is the most important thing about GPR, that you understand what you are getting from GPR as a raw data is not depth. What you are actually measuring is time. Because then you will understand what I mean going forward. So again, you can you use your GPR. It is transmitting the waves going through the surface and the subsurface of the layer. At every subsurface, you have an amplitude. If you then imagine you are taking this wave on the middle and you are moving your device on the longitudinal direction of the pavement, then you look at a cross section and you will have something like this. So every wave is basically representing the interface between two different materials. And what you are looking at in the z direction is actually not the depth, it is the time. So how we get to go from time to depth with GPR, because I'm not actually interested in time, as you can imagine. What I'm really interested in is to know the layer thickness, right? So every material has a property called the dielectric constant. And there are some equations knowing the dielectric constant that can transfer us from what the GPR reads, which is time, to what we are really interested in, which is the pavement thickness. So let's go a little bit deeper into that. So D, which is the depth of the layer, is equal the velocity multiplied by the time over 2. So what do we need to know here is the depth. What we really know is time. What we don't know is the velocity, right? I know I know the time, but I don't know how fast did it go through it, right? Because I don't know I don't need I don't know the depth. So D and V are both unknown in this equation. However, if I told you there is another equation that tells you the velocity of a wave going through any material is equal to the light speed over the root of the dielectric constant, then if we know that dielectric constant is actually a material property that we can calculate, then you can calculate the V. And if you can calculate the V, you can then calculate the depth. So your final equation will be basically D is equal 3 multiplied by 10 to the power of 8 multiplied by time, which you get from your GPR, over the square root of the dielectric constant, which is a material property that you can even assume or have one core taken from the pavement and determine the dielectric constant. So sorry, I didn't mean for this lecture to go like deep, but I think this equation is like simple enough. You measure time, you know the dielectric constant. With these both, you can calculate the pavement depth. So there are two actually types of GPR. There is a 2D GPR, which basically, if you look, you have like on the left-hand side here, you see this orange. This is like an antenna, which basically has both the transmitter and the receiver, and it is shooting like a cone of waves right under the antenna. You can actually have this antenna when you talk about waves, you always remember like there are frequencies. So you can have one antenna or with one frequency, or you can have two different antennas with two different frequencies. If you look at the second image here, the big orange antenna is what we call an air horn, because basically it is a little bit in the air. It is not that close to the pavement surface. Usually it is at 2 gigahertz in terms of frequency. The higher frequency you get, the more precise is your measurement, but the less it can penetrate through the pavement. This is very important here. So if you have an antenna and it has high frequency, it tells you, it can tell that the pavement thickness is 2.4 inches, and it will be very accurate. But if your layer is like very deep, maybe 2 feet or more than 2 feet deep down, the signal will die before even reaching this deep. So it will be very good at giving you a precise estimate of your asphalt thickness and base layer thickness, because it has high frequency. The other one that you see here, we call it a ground coupled, because it is like really very close to the ground, and usually it has a lower frequency, around 400 megahertz or 500 megahertz. This one will not be as precise. It will not give you a thickness of like 5.2 inches. However, it can go really deep, maybe up to 4 feet. So if you have a thick pavement section, you will need both. You will need one, the air horn, to give you a good estimate about your asphalt layer, and you will need the ground couple to give you more estimate about your deep layers, maybe like the sub layer, subgrade, and so on. Sub base. And sometimes you are interested even in having like two wheel paths. So instead of having just one 2 gigahertz antenna, you have two 2 gigahertz antenna. And maybe you can even do this to let's say, even if the lane itself has no big variation in the thickness, which sometimes happen. Let's say you want to measure the thickness of the shoulder and the thickness of the lane, but in the same survey. You have like a big project, maybe it's 100 mile, and you don't want to drive twice. So you can drive with the line between the shoulder and the lane between the car wheels, and you get data from the left-hand side from the shoulder, and from the right-hand side you get data from the lane, and you do the job by just one path. Give me 1 second. I just need to add my charger.
Sure.
Sorry about that. So you can have two antennas at two different frequencies for an obvious reason, or you may have two antennas at the same frequency but at two different wheel paths for a different reason. So what you will get from the 2D GPR is a 2D screen like the one that we are looking at right now. And I will explain further how to interpret data from this image. The other thing is the 3D GPR. Give me one. Sorry, I had some noise coming here. So if you look at the 3D GPR, it's 3D in terms of two things. In terms of space, you can see the antenna is occupying the whole lane. So you can, instead of getting data only on the wheel path, on one wheel path, you are getting data from the whole lane width. And if you even look further, the frequency itself is fluctuating. So the same antenna, instead of being at 2 gigahertz or 500 megahertz, it keeps it changing the frequency. So it gives you both being precise and also going deeper. And of course, it's way more expensive equipment. So what you will get here, you get a 3D shape. You get the same image you get from the 2D GPR by looking on the side of the pavement. So if you have like depth on one axis and distance on the other axis, you can see the pavement profile, which we will go through in a little bit. But also you can imagine that now you can walk into layers, like not just one image of these two. No, there are multiple. Like you are moving laterally inside the pavement. Other way to look at it, if you are looking now from a bird's eye view, you are getting a GPR for everything. To imagine it even more, if you have some pipes inside the pavement, you can actually see them. You cannot get this image on the right hand side with the blue and red pipes from a 2D GPR. You have to use a 3D GPR to get an image like that. Another way to look at it, if you look at this figure on the bottom right hand side, so you see like a 3D GPR wave, and you can jump from a slice to another and know exactly what's happening in the pavement. So what I would be focusing on as the rest of the lecture is how to read and analyze data coming from a 2D GPR. So what you are looking at here is a typical pavement section from a 2D GPR. On the right hand, on the x-axis, you have your distance, basically the travel distance. And on the z-axis, you will have the depth, which actually not depth, it's time, but we will call it depth for now. Okay, so from the surface to the first wave that you are looking at, this is your first interface. So the first black wave that you are looking at, this is the interface between first layer and second layer. And then the first layer thickness will be all the way from depth of 0 up to this layer. And then the second wave will be basically your second interface. So this is the interface between layer 2 and 3. And from the first interface to the second interface, this is the thickness of layer 2, obviously. So if you are using a 2D GPR, the most famous software to analyze the data will what we call Radan 7 from a company called GSSI, which basically is the one that is the biggest producer of 2D GPRs in the US, basically. So when you collect the data, it will come something similar to what you see on the very left-hand side. It is like a little bit of vague and not clear yet. Then you use the software, you play with what we call the color tables and the color X forms. Maybe you also do some filters until it is like shiny and clear the way that you are seeing right now. You can even change the color. I myself like the bluish color on the right-hand side. So this is step number one. You apply some filters and you play with the color gains and screen gains until your eye feel comfortable seeing the interface. Where are these noise coming from? Remember, this is a signal, especially if you are using an air horn. It's in the air. So if you are using your cell phone while collecting the data, or you are passing by a cell phone tower or a radio station, or your radio was open on the truck while you are collecting the data, all of these are causing noise to the GPR data. So the software here will help you isolate this noise. So what you are seeing is only the data coming from the pavement. So you have two options inside the software once you determine your interface. First one is called easy track, and you literally have someone clicking with the mouse inside the layer. You don't need to, like, not every one of these red dots are like just one click. You can click like in the beginning and at the end that it will interpolate the dots in between. But the closer you keep your hand to, between clicks, the more accurate this interpolation will gonna be. Something interesting here to look at is the wave itself. Let's say in the middle, it is I don't know if you see my mouse cursor. It is like black, white, black. So the part in the middle is white. So this is what we call a positive wave. A positive wave means if we go back here at the very beginning, you see these amplitudes. If they are on the right, the wave will always be black, white, black, with the white being in the middle. So we call it a positive wave. And if it is vice versa, if it is on the left-hand side, it will be white, black, white with the black in the middle. So what does it mean to have a positive wave, and what does it mean to have like a negative wave? So if you are going from a stronger material to a weaker material, you should see a white wave. So if you are going between the asphalt and the base layer, you should see a white wave. But if you are going from a weaker material to a stronger material, this is a negative wave, and usually this will be black wave. You may ask, okay, why flexible pavement or even rigid pavement, always the stronger material is in the top and then the weaker is in the bottom. I should always only see white waves. That's actually, this is true only 90% of the time, because you of course have heard of a composite pavement. So if you are doing a composite pavement, you have asphalt on top of concrete. So actually, at this case, the interface between the asphalt and concrete will be negative and your wave will be black, because basically concrete is stronger than asphalt. Other way of interpreting the data is just to highlight a block where you feel confident that this is the interface, and you just ask the software to add points and you fill it. Once this is filled in the software and you already has highlighted all the interfaces, remember, this depth that you are looking at, this 10 inches, that if we say like this red dots are around 10 inches, this is not accurate yet, because it assumed a directed constant that's the default in the software to calculate the thickness, and that's why you see that the layer here is like very noisy, like of course it is like fluctuating a lot. So by having one core, you add the ground truth. So you tell the software that actually at this specific location, the thickness of this layer was 6. Once this is done, the software will calculate the directed constant and will start calibrating it. And now you will see how this fluctuation in the layer thickness is gone. So first step, we will go through the steps again one by one. I will summarize them. So once you have the core, we call it like a ground truth, and you insert what is the core thickness. The layer, this is what we call a GPR calibration. And if you imagine before GPR, if you have 1 mile, people used to take a core every 10th of a mile. So these are 10 cores, which are very expensive. Now with the GPR, it is recommended you take 1 core per mile. So the cost has been reduced by 90%, basically. This is an example from a fake signal. As I mentioned, this fake signal can be coming like from a radio station or a cell phone tower and so on. And by applying some noise removal, you can basically remove it on the right hand side here. So to summarize, number one, you remove the noise, you select the color you like, you add the dots, which basically is the interface between two different layers. You add a core, which basically is this black dots that you are looking at here to do your layer calibration, and then you are done, and you can transfer to the client if you are doing a consulting business, or if you are even doing it in-house. Something like that will be the final product. You have your milepost or stations on the x-hand side, on the x-axis. On the y-axis, you have the depth in inch this time because you have already done your calibrations. You can even add the cores on the pictures, sorry, on the charts, and make sure that the cores are on top of the lines, which means everything is calibrated, everything is making sense. When I look at the thickness on the core and the thickness of the GPR, they are giving me the same exact thing. So this will be your final deliverable in top of maybe like a spreadsheet also, and so on. Usually every 1 foot, which basically yeah, 30 centimeter, right? And then we summarize it and take like what we call a moving average every 100 feet. Another application of the GPR, of 2D GPR, is not just the pavement layer thickness. If you are looking at these hyperbolas in the shiny ones in the middle, like the ones that has like the magenta dots, this will be your rebars basically. So you can actually use GPR to determine the thickness or the depth of your GPR if you are testing in concrete, reinforced concrete pavement, or if you are testing in on a bridge. You can also see here, like if you have like this black wave, but it is not all over the place, just in a specific location, it's a very good indication that you have a void. So you are losing material in this very specific segment of the pavement. So I'm ready for the questions, and I hope we learned something.
Excellent presentation, Dr. Omar, and I really enjoyed it. Very interesting information, a lot of new knowledge, at least for myself. Excellent points for like young researchers to work on, or if somebody wants to start, like as you mentioned, some of new ideas to maybe like start up some business. There is a lot of, or plenty of knowledge here in what you have presented. Thank you very much. Thank you.
Well, thank you, Doctor. Thank you.
So we are waiting for some questions, and don't let me choose some people to ask, or ask them to ask questions. I believe we have some colleagues from American University. I've seen Maram, but I'm not sure if still there or not. And also Dr. Mines, if she's here. Dr. Mines, do you have any questions?
Thank you very much. Actually, it was very interesting for me, and I have written a lot of notes, and I think I can do more research about it and see, because you said already there's something that's already been explored in the state. For me, everything was new, actually, although I lived in the state for a while, but it was very interesting. Thank you very much, Dr. Omar.
Oh, thank you. I'm glad to hear this feedback. Thank you.
Dr. Ahmed Mutwalli.
Thank you, Dr. Omar. This is a very interesting presentation. Actually, we don't have experience with GPR here in Egypt. I think we have an opportunity now to look for new insights and new research topics, like using GPR in our research and its application in pavement layer thicknesses.
I actually no. We have a couple of GPR equipment. I believe Cairo University Faculty of Engineering, they have one, and I think
the German University have one.
I'm sure that German University also have one. and I was on a committee for one of the students at Cairo University, and he did some work. It was mainly related to like pavement management system, but he used the GPR on one road and collected the data and interpreted the data and used it for his work. So yes, we have a couple of these equipment. Now they are very expensive. We were planning to buy one at our school here, like maybe 2 or 3 years back, but the prices went really high. So this project is still on hold, but we should put it in our plans. Yeah.
Wonderful.
Okay. We have also Dr. Hilal and Dr. Ali from University of Sharjah. Hilal, do you have any questions?
Yes, I'd like to say that this is a very, very presentation, and thank you, Dr. Omar.
Thank you, Dr. Hilal.
I've been lucky to meet with you in University of Sharjah,
Of
I
course.
think a month ago. Yeah.
Oh, it was in May, and it was a great hospitality. Like, thank you very much.
Yes, yes. I'm very happy to see you and hear you again. And yes, it's this opens a lot of things for the future, actually. Like we should do more research on those, and I think especially in the Gulf area where they have more fund. And I think we have a project with Tensor, and this project have been pending for a long time, but such technologies will be very interesting. So I'm very excited for the future of those. Thank you again.
Thank you, Dr. Hilal. Thank you.
Ahmed Mu'nis. Ahmed, are you with us? Dr. Alaa, do you have any question or comment?
No, Dr. Sharif, I have no question, but Dr. Omar did a great job. I really enjoyed it. He mixed it between academia and industry. Of course, he did a great job for this mix. It was very fluffy. It's like a dinner we eat today, Dr. Omar. I
Thank
really
you,
enjoyed it.
Thank you.
Thank you very much.
Heavy meal, but it's nice one. Omar,
Yeah.
now I remember that I took from you like this large amount of data on one of my external hard drives, and I totally forgot about it. That was
Yes,
long
yes.
time ago.
A TRB 2020, I guess.
Yeah, wow. So it's been like 4 years.
Yes.
And I totally forgot about this data, and we should think about it and how to make use of it.
Yep.
Okay. So
Thank
when
you,
we have
Dr.
time,
Very
let's discuss about this and see how we can like start working on some research papers out of this data.
Sure, yeah.
Okay. One more question. Abdullah.
Hi, thank you, Dr. Omar. Again, more information about pavement investigation techniques, and thank you for this exciting presentation.
Thank you. Thank you.
All right. I guess that was really very interesting, Dr. Omar, and I really appreciate your time and effort putting all this information together and presenting it in such nice way and very interesting way.
Thank you, Dr. Sharif,
right.
Just wanna say thank you to everyone who have attended today. Thank you for Ahmed Naguib for coordinating. And I mentioned in the beginning that Dr. Sharif and Dr. Ala are my teachers, and I didn't know that Ahmed Awad was there. So he is my teacher too. I have to say that, and thank you for everyone. I have been honored to be with you today.
It is our pleasure, Dr. Omar, and that was really very enjoyable. And we look forward to more presentations in the future.
Sure, yes.
Okay, and let's keep in touch, doing some research work in the coming, maybe in a month or so, we can meet together and start talking about research. Okay.
Inshallah.
Great. شكرا لكم جميعا يا شباب، ويعني ان شاء الله نتمنى الحضور دايما، لان في معلومات مفيده زي ما انتم شايفين. انا شخصيا استفدت كتير يعني. شكرا لكم جميعا على الحضور، وان شاء الله نشوفكم بقى السبت اللي جاي باذن الله. السبت اللي جاي مش هيبقى اونلاين، هيبقى في الجامعه، صح يا دكتور احمد؟
ان شاء الله يا دكتور شريف. بس هو دكتور احمد متولي يعني اداني تعديل كده ان يعني الاونلاين برزنتيشنز هتبقى في قاعه دكتور رشاد البدراوي، فده هيدي الحقيقه مكان اوسع وافضل يعني.
طبعا انا يعني بدعو الجميع اللي يقدر يحضر عندنا في الجامعه ان شاء الله الاسبوع اللي جاي يوم السبت. احنا عندنا مشروع بحثي مع جامعه اخن في المانيا، وجاي 4 من الريسيرشرز هناك، هم مينلي طلبة دراسات عليا يعني في مرحلة الدكتوراه والماجستير، هيقضوا معانا كام يوم. فيوم السبت احنا مخصصينه علشان نسمع منهم عن شغلهم، وبرضه هيبقى فيه برزنتيشنز من الطلاب بتوعنا. فطبعا الدعوة متاحة للجميع، أي حد يشرفنا إن شاء الله. هيبقى يوم السبت اللي